Hello guys. I was walking around here in this area and I came upon this quaint little town. Apparently it is called Green Village. Oh no, rain. God damn it. Well, it's raining. Why are you standing out here? Get inside. You're gonna catch cold, you know. Well, let's just pretend it isn't raining, shall we? So this little village here, out on the border of the desert, Green Village, apparently. If you don't get the reference in a minute, don't worry, it's not important. Because apparently there is some kind of fenced off area here. What do we have? Area 52? Right, out in the middle of the desert. And yeah, I was being lazy, I didn't want to fence it off. Shh, would you be quiet? I'm trying to talk here. Fence it all off at the moment. Well, the point was that we were going to be talking a bit about redstones. Whoa. Oh my god. I think I just move a bit away from here so we don't have to deal with the storm. Right. Redstone. Redstoning or redstone circus. What is that all about? You might hear some people talk about gates and whatnot, but let's just start with the basics then. No, we do not want to have a thunderstorm right out in the middle of the desert. Well, normally you would put a level like this or button, and you would use it to open a door or something like that. So, door closed, door open, door closed, door open. But what we also can do is we have this redstone here. See, if I just lay it out in a line here, what will happen when I flick the switch here is that the redstone will get some sort of power current running through it, as we can see. And we can do all sorts of cool stuff with this. The problem is getting to know what. That's just so annoying. I'm getting so distracted by that. Oh well. Well, anyways. What we can think of is that we have like a power switch that could be on your computer or on the wall or just about anything else. And we have like electricity running through here. Right. So, what does that give us? That gives us part 1 in our little setup. That is, we have a way to power things. But we also have another way to power things, and that is with the redstone torch. Now, as you can see, this little thingy here, it's just like always on, and it just powers stuff. And see, what's the point of that? Well, this little thing here, if we put it like this, and that one on the other side. And what happens when you flick it off, and this one flicks off? That's nice. That's nice. What if we do... Oh, sorry. Do this. So it's on, but we don't get any power to it. Now we try to... Oh, sorry. You know what? I think I'm just going to expand this one just a tad so you can see that the power is actually running from here into this block, so to speak. And we want to get it a bit further. So if I push my button, our power starts running here into it. Oh, but this one turns off. What is that? So let's turn this one off. So it's off, no power. But this one is on. So that means that when we have power on, when we have a current going into our system, we have no current coming out. But if we have no current coming into our system, we have a current coming out. That is a basic gate. That is actually a very basic gate called a NOT gate. And a NOT gate is the exact same thing as a transistor, more or less, a transistor inverter. They work in a little bit different, because normally you would have something like a power current running from when you start your computer, and this one would be powered, so to speak, and it would run into the actual transistor, which has 3 legs. It has a collector leg and a middle leg and a base leg, and like here where you would have your your middle leg, this one would go into, this would be grounded, so to speak. Can make a ground signal here, actually. No, can't do that. But anyways, so that would go to the ground, and this would be your power. When you power on your computer or something like that, you would have current running through the computer down in your motherboards, and this one, that current would run into your transistor, and this piece here would be grounded, and depending on what kind of voltage you would put into your base leg here, the transistor would act as either as an infinite resistance, and your power would go that way. That is on the collector leg, your voltage out, so you will get, if you do not power your transistor, this one acts like a huge resistance, so your current would take this route over there. But if you actually power this thing, your transistor would open up, so to speak, and you wouldn't get any current running here, because electricity will always want it has one purpose in life, and that is going to ground. So it would go down to ground in that case. And the basic is, if you have current coming in here, you will not have current coming out. But if you do not have current coming in here, you will have current coming out. And that is your basic transistor, and that is your base block when you're building. It could be a computer, it could be any kind of computer, a household calculator, or greeting card playing, season greeting card playing, Merry Christmas songs when you open it or something like that. The idea is, when you have power coming into your system, you will not have anything coming out here. And when you do not power up, you will have something coming out here. And that is basically what we refer to as a NOR gate. Not gate, of course. I'm getting ahead of myself here. A NOT gate. Anyways, a NOT gate, or a transistor, inverter, you could actually, depending on if you, let's just see if I can illustrate it again. Like we have here, and we have this one coming in. So this will be going to the ground, and this here would be our power source, so to speak, and our input and our output. Right. So, depending on how we actually wire these, this is one transistor. So instead of this going into the ground, I am going to power it in a... Oh, sorry. Yeah. That ground. So we have two inputs here and an output over here. So we have actually taken our transistors here and we have connected them in serial. Yeah. All right. Yeah, it's cascaded in a series. It's been a while. I did study this back in college, but it's been quite a few years since I was in college, so please bear with me. Anyways, we have two inputs here. We have this one, and we have this one. And if we do not power our transistors, they are acting like a infinite resistance, so to speak. So we have our current coming from here, and it's going to... I can't really get that way, because this one here is bugging me, so I will run this way. Alright, so I'm going to power on here. I'm going to set it, so to speak. Now current is coming in here, and because we have it powered on, we can move this way, but this one isn't powered on, so we can't really pass here, so we are going to back and go out this way. Right, remember, electricity will always try to head for the ground. Alright, so what happens? I'm going to power this one also. So we are going to come this way. I'm going to head for the ground. This on power, so I can move past this one. This is on, so I can move past this one. So we are coming to the ground. So we are getting no voltage out of this one. So with two transistors in a series, we have two inputs, and we will get an output here on the occasions if this one is off and this one is off, or if this one, or if this one is on but this one is off, or the other way, or the other way around. If that one is off and this one is on, the only way we can actually turn this off is if we have both of these powered. So we'll call this one, okay, call it A. Yeah, let's get that one A. So that's A. And this one is B. So A and B, and over here we will have X. Right. And we can make a little table. Remember from when we had 1 here, if we had 1, that is only A, we will have a table saying that we have A and we have X. Right? And if A, that is this one here, running here, if it didn't have any current here, the current would, this one would act as an infinite resistance, so we would get a current out at X here. But if we actually powered this one, if we actually put a current in A, the current would run to ground, so we wouldn't get anything out of this one. So if A is 0, X would be 1, and if A is 1, X would be 0. The NOT gate, right? The NOT gate. Let's put that there. NOT gate. Right. Now we cascaded these into in series here, and what we have discovered is that if we have A and a B and the X, right? So if we didn't have anything, so if we did not power this one here, that is A over here, so if we did not have anything here, and if we did not have anything here, so to speak, we would have a current going out into X, so that would be a 1. So likewise, if we did not have anything here, but we had a current here, it couldn't still move here, so we had to move back. Sorry, that actually was the other way around, because this one is blocking it, so to speak, so it will never come past here, it would just run out into X. So we will get a 1 in X, and if we turn this one off, or that is, if you actually put a current in here, so this one wouldn't act as an infinite resistance, but would allow a current to run through it. So turn this one off, and this one, but if this one was still turned off, we would have to go back, and we would get a current out into there. So actually the only way that we could get our current turned off, so to speak, at our output signal X would be if we had both of these powered like that. 001 once. That this here is a oh my god, it's been way too long, but it's called a truth table. So so this one would actually always, and see 0 is false and 1 is true, so this one is always true unless both the inputs are true, then the output would be false. That is called a NAND gate. Yeah. We need one more building block and we're ready to go. And how are we going to do that? Well, we had our NOT gate. And then we made our NAND gate, which stands for NOT AND, because in the way, you know, the logic works, as you can see, it's not AND. If it were, it would have been the other way around, so to speak. So it's not AND. How can we make it an AND? Obviously we can just take that output here and put a NOT gate at the output. To invert it, we will get a AND gate. So if we NOT the NAND gate, we will get an AND gate. Right. And basically you can actually build a computer out of this. I mean, this is the basic, the building blocks you get when you build, when you build computers. There is one more we can look at, and then we'll be done. We took this NAND gate, and how did we make it? We took 2 NOT gates in a series to get a NAND gate. But if I didn't make it in a series, what if I did it in parallel instead? What would we then have? Like, if I have my current coming in here, my system's current, so to speak. I don't know if I have enough room here. Let's see. Oh, sorry. Right, we have a system group, but we want to do it in parallel, so we're going to do it like that. Like that. That wasn't it. Like that. So instead of in a series, like here, where it's first that, then this, we're going to have it parallel, so our output will be here. This is where our X is, so to speak, up there. And this is the N. And then we will, instead of having 1 going to the 1, we will actually make this one there, not that one there. It's a tad too long. So this will be grounded, and this one will be grounded. I'm just going to make it a bit smaller than that because there's not enough room. And we'll have an input coming from here, and we'll have an input. Okay, I'm going to make it over here. Doesn't matter. So we have an input here. And here, this one could be, we could call this one, that could be A, and this one over here is B. So we have the A input and the B input, and we have an X here, the output. And we have ground here, and the system current there. So the system current is going to come down here, and it wants to go down to the ground somehow. But if this one isn't on and this one isn't on, we'll have to go over here. But if I did power either of these, we could head into the ground. Either here, if this one is on, we could come down here, or if this one is on, we could go down there, or if both are on, we could also come down here. That means, if we take it in this truth table, that we will have a and a B, whoops, A, B, and X. So, if both A and B, there were no power on A and B, we would head out to our X because we couldn't get down to the ground, so to speak. Right. But if either A or B were on, let's put A, B on here, we could head down to the ground, so we wouldn't. What's happening there? Let's see. Yeah. So we wouldn't actually head out at X. Likewise, if this one were on, whoop. Know what my keyboard is doing at this moment. And the last one, if both are on, we wouldn't. Damn. I think I got a problem with my 0 key. Oh well. So, we would actually only get to have a current over here in the case that both of these are off. And since it's not that or that one, not nor, we call this is a NOR gate. And if we take the output over here and we put the NOT gate on it, so we NOT our output, we will get an OR gate. So we actually, from this one NOT gate, if we put them in a series, we will get an NAND gate, and if we put them in parallel, we will get a NOR gate, and if we NOT the output of these, we will get an OR or an AND gate. That is, we have five building blocks, so to speak. Actually, since obviously you will need a transistor more when you build, if you want to build a computer from ANDs or OR gates, you would use these basic ones like a NAND gate or a NOR gate. But when we are building stuff and talking about stuff like this, it's easier to use the entire spectrum, or so to speak. Yeah, and how does that work with Redstone? Right. So we have our voltage in here, our A, and our voltage out here, our X. So if this one is 0, we will get voltage out, and if this one is 1, because we didn't get a 0 out, that is our NOT gate here. Here's the truth table from our NOT gate, and that's the compressed version. You could probably look this one up on the wiki or something like that. Likewise, over here we have our V1, our A, our voltage in here, and our second voltage in here, our B. And over here we have our V out, our X. So, and as you can see, this is a NOT gate. It's built from this. It is built from this. We just have two of these. So if I flick this one, so we have a 0, 1, 0, 1. That is a 1 out here. Okay. Let's see, we turn this one off. Likewise, if I switch them about, we still have a 1 over here. But we take both, these goes out, and we have nothing over here. That is, I didn't actually make the truth table for this one, did I? I should. Let's do that. Let's do that. So, we're going to be needing two. So we have A, B, and X. We have an A, and then B, and then X. Right. A, B, and X. So if we take here and we start with this, right? We have A at B. So if both of these are 0, our X will be 1. So A and B and X, both of these are 0. I do have a problem with that one. That 0 there on my keyboard. Apparently, I have a 1. So far, so good. Right. So if our A is 1 and our B is 0, we have a 1. And the other way around, if our A is 0, our B is 1, we have a 1. So the only way our X will be a 0 is if A and B is 1. Let's do this. A, B, and X. So A is turned off and B is turned off, then X will be 1. Likewise, if this is off, this is on, this one would be on. If this is on, but B is off, our X would still be on, and it would only be in the time when both our A and our B is 1 that our X will be off. What does that remind of? That is a NAND gate. And here we have the compressed version of the NAND gate. So both of these are on. Just to show you how it's connected here. Yes. And this one. Yes. So the only way we can actually turn this one off is if we turn both of these on. Then your redstone torch will switch off. So when you turn that one on and this one on, both of these will switch to off position, and we will get a 0 out of this one. So I'm going to turn This one is off, so that is on, because it's like a NOT gate. Likewise here, since it's, whoops, that. And now you can guess what we have here. What do you think that is? So both of these right now are off, and get this one on. Okay. Boom. This one. So we need them both to be off before we actually get a current. Does that sound familiar? Both need to be off before our X is off. Oh yeah, that's the NOR gate we have here. So in Minecraftian terms, we will refer to this as our NOT gate. This as our NAND gate. And this is our NOR gate. And the theory is you either pick one of these, or you pick one of these, and this one, so you can take that one and this one. Oh my goodness. Not this one, that one. And you have these two, you can build a computer. That's how you build computers. So you can build a computer in Minecraft. But before we get to that, let's have a little bit of fun. Oh yeah, but not that it isn't fun to build a computer, but it might be a bit tricky to start building a computer right away. So I am thinking we are going to have to play a little bit with perhaps some other gates. Yeah, well, why don't I quickly show you what you can do with gates? And let that be, let's see if I can remember, perhaps, no, not there, not there, not there, not there. I wonder where, perhaps there? Sorry about this. I had a little idea. What is that? No. Not that one. Sorry. Gonna take this one. It has to be this one. I'm pretty sure it is. If it isn't, we're gonna just cut the show, so to speak. Let's have a look around. Let's have a little bit of a look around. Of course, now remember. Yeah, and that. Yeah. Let's just look what we can actually use these gates for. There is one more thing we should talk about. I haven't talked about it yet. I'm going to show you it here. Here. This repeater here. We'll get to that. It's pretty important, but it's not going to. Let's check this one out. You've got some glowstone down there. Of course, that's just because I shouldn't have built stuff in places where there are ice, but I wanted to test something out, so eventually I just put down some stones so I could get a bit of light down here. The idea is, of course, that wouldn't have these, so from the above it would just look like a... Come on. Oh, yeah. Just walk about. I'll just have a little bit of all this. Yeah, and then if you can... Don't look at these stones, you would just have something that would be a normal looking little pond, so to speak. If you pop down here, that one should just be gravel or dirt, but... Do I make it? Can I make it? I can make it. Whoops. What happened? Oh, there's something happening there, right? Ah, we can make it, we can make it. Ah, we can do it this way instead. Ah. So actually we have a secret base inside here. I'm going to... Come on. Put down this bit. You can see what actually goes on down here. There's a bit of a delays here. So this is one of the possibilities you can do with stuff like this. Of course, there's no memory or stuff like that. This is all just logic. Gonna make it look neat. Do have one. I wasn't quite satisfied with this one because I wanted it to open. You get in, it would close, the water would disappear, this would open, and you would get out, and it would close. And likewise, if you are standing over here, you would push that button, it would open, you would get in, it would close, this would open, and you can go out into the water, like an airlock, so to speak, instead of this one here. That is a bit more tricky to do. Get out of here. Whoops. And you can see this one is broken. Let's see if we can fix it just for now. Or if it's completely messed up. I wonder what happened here. The thing is, sometimes I have the kids playing on the computer, and especially this one here isn't actually. It shouldn't be there. It shouldn't be there. It shouldn't be there. So what we just need is to connect this one to a button, so to speak. Last one. That's it. One, two, three. One, two. Can we put a button? Oh, there. Button. No. Probably need to have one more down. Yeah, should be one more down. That one. Put that one there. One there. Like that. Right? Yeah. Get it in here. That one close. This one open. And close. Like that. Yeah. That's like a real airlock. Of course, this could be built like the one over at the pond, just for looks. And here we have it all. How it works. The delays and everything. And how it crosses over depending on what side. And we will get to this. See, we actually have a memory over here and a memory over here. And how it all works, we will find out. But let's call it for today. Hey!